Hello everyone, it's Ms Redmond here and welcome to the third lesson in the sound topic. This one is called How Do Sound Waves Transfer Energy? If you haven't got one already, please go and get a pen and a piece of paper so that you can make notes and do any of the little tasks that I give you as we go along. Here's our learning journey at the bottom. Feel free to pause the PowerPoint and write any of those points down. Little recap for you on states of matter then. We've got a diagram here showing the solid particles all tightly packed together, liquid particles, all of these should be touching really, and the gas particles all spread very far apart. So my question to you is, can sound travel through all of these states of matter? And you need to justify your answer, so yes or no and why. Feel free to pause the PowerPoint while you have a think, and we'll explore this idea a bit more on the next couple of slides. So, what can you hear when you're in the swimming pool? If your head's all the way under the water, can you hear sounds? Can you hear sounds in the same way as you can when your ears are above the water? What's going on and how does that relate to the particle diagrams and the question that I asked you on the previous slide? And then have a look at this one. I don't know if you've ever tried this, tin can phones. There'd be another person on the other end of this string. How does this work? If I've tried it and it didn't work very well, but it did work. So what's happening to the sound wave? How is it getting from one person to another? And again, how does that relate to the states of matter diagram that I showed you on that slide? And the question, can sound travel through all of those states of matter? And then think about how dolphins communicate. So they spend all of their lives in water, most of their time under the water, and how do they speak to each other and communicate, how they hunt and how do they socialize, and how does that relate to the question, can sound travel through solid, liquid and gas? So you might gather from this slide that yes, sound can travel through all of those different materials, okay? Because all of those materials are made up of particles. So all three states of matter, solid, liquid and gas, are made up of particles, and sound requires particles in order to travel because it's a vibration. So in the air, the speed of sound is 340 meters per second. So pretty quick. However, in water, it's even faster. It's 1,500 meters per second. So air is a gas, mixture of gases, water is a liquid, and steel is a solid, is a steel bridge. The speed of sound in steel is even faster than those previous two. It's 5,000 meters per second. So can you tell me what the pattern is and what's causing that pattern? So write down your ideas. Pause the video and write down your ideas and we'll get into the answers in a moment. And if you want a challenge, what would a sketch graph of this pattern look like? So that's a pretty challenging maths related challenge. And this is the answer. If you had the density of the medium along the bottom, so increasing density in this direction, and if you had the speed of sound up the side, so increasing speed of sound, you'd have a graph that looks like this. So as the density of the medium increases, the speed of sound also increases. So down here, if the density of the medium is 0, so if it's a vacuum, speed of sound is 0, sound can't travel in a vacuum. But if the density of the material is very high, then the speed of sound is also very high. Here's the answer to that question. So the more dense the material, the faster the speed of sound. And that's because the particles are closer together, so they bump into each other more easily and more often. Here's a little example to get you thinking about the speed of light and the speed of sound. So thunder and lightning happen simultaneously. They happen at exactly the same time. So how come we don't see and hear them together? We always see the flash of lightning first, and then we hear the roll of thunder. So pause the video now to think about why that might be. We'll talk about it on the next slide. So here's your answer to that conundrum. The speed of sound in air is 340 meters per second, but the speed of light is 300 million meters per second. So light actually travels 1 million times faster than sound does. And so that's why you see the lightning before you hear the thunder, although they actually happen at the same time. It takes longer for the sound to reach you than it does for the light to reach you. And you've got a link there to show you how to calculate the distance of a thunder and lightning storm by using these two facts. Okay, here's a little gap fill for you to do. Have a go at those, and I will show you the answers on the next bit, so feel free to pause the PowerPoint now and write those down. And here are your answers. All sound is caused by something vibrating. Sound travels through air or water or solids by waves. Sound waves cannot travel through a vacuum. On the moon, astronauts use radios to talk to each other. This is because there is no air on the moon. Sound waves transfer energy through the particles in gases, liquids, and solids. Sound travels faster through water than through air because the particles are closer than in air, closer together. And here's your summary. A vibration is a medium moving back and forth or backwards or forwards and back. The medium is the material or substance that a wave travels in. A vacuum is an empty space with no particles in it. It's another literacy point, because we use vacuum to mean hoover that we use to clean our floors. But in science, a vacuum is an empty space with no particles in it. The speed of sound is 340 meters per second in air. It's 1,500 meters per second in liquid and 5,000 meters per second in steel. And the speed of light is 300 million meters per second. Thank you very much for listening, and I will speak to you next time.